Hello. So, in this video, we're going to be talking about limits at infinity. So, in general, we're going to sort of go through what that means and what it doesn't mean specifically. But sort of as a place to start, we want to think about sort of what we know about limits so far. So, limits, remember, don't care about a function's value at a specific point, right, a specific x value. Rather, they attempt to sort of capture the behavior of the function at that specific x value. And this is true for finite x values. So when we start talking infinity, as is pretty much always the case when infinity comes into play, things start to get weird. So another sort of common way that we use limits, sort of explicitly because things get weird when we start trying to introduce infinity, is with infinity, right? So we want to talk about limits at infinity and when limits equal infinity and sort of what that means. So in general, limits at infinity are sort of, they're very similar, right, to limits at a point, but there is a fundamentally sort of different thing going on. It's a fundamentally different concept underlying that. So to understand why, sort of as a quick review, right, infinity, we sort of conceptually have this idea of infinity being something very big, right? Like we say, when we say infinity, people usually think of very large numbers, but that's a useful intuition in many cases, but here it's really important to remember that really what infinity is this idea of growing larger and larger, right? So infinity already isn't a point. It's not a destination. It's not a value. It's an idea of growing more and more and more, right? It's a process. So when we talk about limits at infinity, it's not really limits at a point, right? Because infinity isn't a point. It's this idea. So really what we're saying when we say a limit at infinity, this is a shorthand for this sort of limiting behavior. What we're really talking about is the behavior, right? That's what limits look for as things are going toward infinity. So the important part here is that infinity is not a point, it's a behavior. And so when we talk about limits at infinity, we're talking about behavior, not a value, right? So taking a limit as x approaches infinity, this is the process of trying to determine exactly what that value of the function, right, what that function is doing. So what, as it gets sort of closer to as the input gets bigger and bigger. So you sometimes will see this in like textbooks and things as arbitrarily large, but you can think of it as basically as the value gets bigger and bigger and bigger and bigger and sort of way bigger than anything you would even think about, what's happening on the function. That's what that limit is trying to capture. And a lot of the times, to be clear, this isn't necessarily a finite value. It's not like when you take a random function and you put in gigantic inputs, you're always going to get some nice small number as the limiting behavior. So like a really easy example, this limit of x squared, clearly, as x gets bigger and bigger, squaring it gets even bigger. And so you don't have a sort of finite sort of destination always. So as we saw just a second ago, this limit notation is the same sort of notation that we use, right? So we would say, when we want to say, take the limit of f of x as x goes to infinity, we sort of write this in x going toward infinity bit down here, just like we did with the numbers. But this is what mathematicians call an abusive notation, because really this notation is misleading in that it, again, can't be the same thing, because normally what we have down here for the x value is a number, and infinity isn't a number. But nonetheless, we're trying to accomplish the same end goal. We're trying to understand the behavior of the function f as we're doing something. That's what limits do. And so that's why we have this notation, even though it's a little misleading. So in particular, this notation, again, is shorthand for this idea of trying to determine what the function is doing, trying to find the function's output as the input gets larger and larger, right? So when we say the limit at infinity and we write the limit as x goes to infinity, again, it's important to note that this is shorthand. This is sort of just a way of writing an idea where that idea is not quite the same as the normal limits. So looking at an example, we can sort of look at this classic e to the minus x, so a classic exponential function where we've sort of flipped it the other direction. And if we go along this function to the right, this would be, if we keep going forever and ever and ever, this thing tends to flatten out down to 0, right? So we would say that the limit as x goes to infinity of this thing is 0, because that's where it's sort of tending toward as we go further and further and further. Now, if we go the other direction, so instead we go to the left, there we go, forever and ever and ever, this would be the limit as x goes to negative infinity. And here we can see that it doesn't flatten out, right? It would just keep going up and up and up forever. So we would say that this limit is infinity. But again, the sort of important takeaways here, if we take a limit as x goes to infinity, then what we're really doing there is sort of looking at this idea, right? Because taking a limit as x goes to infinity, we don't do this treating infinity as a point. Rather, it's sort of this shorthand, right, for this doing, getting larger and larger values of x and seeing what happens. Likewise, we saw in the sort of last example back there that we can have a limit sort of quote unquote equaling infinity, but again, infinity is not a point. So this is again shorthand for this idea that it's just getting bigger and bigger and bigger, right? So we say that a limit equals infinity is again an abusive notation. It's a shorthand for saying that the function is getting larger and larger, positively or negatively, if we go to positive or negative infinity, as we get closer to whatever that value is. So sort of in conclusion here, I know I've said this a million times, but it's because to date, we have pretty much always conceptually used infinity as a number, and doing that here is almost certainly going to lead you into very bad territory. So we really want to hammer in here that using infinity, we use it sort of in the same context as a point, but it's a mathematical shorthand, meaning that it's this process of growing larger and larger and larger. And sort of importantly, it's not the same thing as treating infinity as a value, right? So at this point, if you sort of try to treat infinity like a number and like try to do computations or anything like that, as we'll see in example videos, things will go very, very wrong very quickly. So we are sort of at the point where we really need to break that intuition and start thinking of infinity as a process rather than a value, okay? So that is that.